Okay, makes sense. Now, in a laser, we use this process to produce coherent monochromatic light, but it's stimulated emission as opposed to just emission. Now, this is what we do, okay? We want our medium, so let's say, for example, we take helium or a helium laser. So we have our medium, and our medium is helium gas. So we have a chamber filled with helium gas, and that's our medium, okay? The helium gas full of helium atoms with electrons in it, okay? Now normally, the electrons in the helium gas would be at, or in I should say, the ground state. We don't want that for a laser. What we want to do is we want to excite all the atoms so they jump, so the electrons are not in the ground state, they're actually in the excited state, okay? So this is not the situation we want. We do not want the electrons to be in the ground state, we want them to be in the excited state. So we want to excite the helium atoms. Unfortunately, that process has a rather unfortunate term, and it's called pumping, okay? So we pump the medium so that our electrons in the medium are no longer in the ground state, they are in fact in the excited state. That can be done by a number of ways. One way is to pass a current through it. So we might have a cathode and an anode connected to a power supply. The other way is to shine a light, okay? Not just any light, it's a very, the process is quite complicated, but effectively it's just shining energy on here so the electrons gain the energy to go to the excited state. Now the special thing here is that we can actually make the electrons stay in that excited state for a little while, and that's very important to get our monochromatic coherent light source. Now what we do is the following. Okay, once we have our electrons in this excited state, we wait for one of them to fall down. When it falls down, it releases a photon. Now, as we know from our work in quantum physics, that photon must have a very specific wavelength and frequency from that equation, E equals hf or hc over lambda. It has to have a very, very, very specific wavelength, okay? Now that photon is then released. As I just said a second ago, we have in our gas lots and lots and lots of atoms which are in the excited state, okay? So here's two atoms in the excited state. My photon's just been released from the first atom, and now it's travelling through the gas. That photon will pass other atoms. When they pass other atoms, these atoms are stimulated into emitting another photon, because this energy of this photon matches these energy gaps. So as it passes through, it stimulates these electrons to fall down to the ground state and also emit a photon.
So does it stimulate the emission of radiation?
It does stimulate the emission of radiation, Mr. Gilchrist.
Fantastic.
Now, not only do we have our first photon that we started with, we also have a second photon which has been released through stimulation. That's a bad diagram. And they go on to the next atom, and again, this one has been stimulated to emit, to drop down to the ground state and emit a photon. And so, as you can see, the photons are building up. Now, the key thing here is that this electron dropped down because this photon came through the atom, stimulating it to emit the second photon. We now have two photons. They go on to the third one. It's stimulated to drop down, emitting a photon. They've all been stimulated emission. Now, the key thing here is, because this energy gap is the same in each case, same energy, same frequency, same wavelength, monochromatic light. And the other thing we get is they're all in phase.
So is that light amplified?
And it's also amplifying the number of photons, so the light has been amplified by stimulated emission, hence laser. Okay, one thing I just want to go back over with you before we finish the video is another key phrase that I didn't say, but just so I don't forget before we finish the video, is I mentioned before that we pump the medium to get all the electrons into an excited state. Now, when you have more atoms in the excited state, when we have more atoms in the excited state than in the ground state, excuse me, ball pen, than in the ground state, we call that population inversion. That's a key phrase that you guys need to know. This is called population inversion. Okay, I'm just going to recap really quickly. Lasers need a medium, okay? That medium, we need to excite that medium to obtain population inversion, where we have a state where the more electrons are in the excited state than the ground state. We can do that by shining light on it or by passing a current through it. After which, we allow electrons to fall down an energy level, emitting a photon. That photon then goes into another atom, stimulating the emission of a second photon, and so on, amplifying the light and amplifying the number of photons. Those photons which have come out, the key thing is that they have the same energy, same frequency, same wavelength. Monochromatic coherent light, which is effectively what a laser is. Okay. Here, lenses.
Awesome.
Done. Thanks a lot. Thanks for watching. Hang on.
Okay, we just realised we missed a little bit. That's brilliant, that's true teaching. Okay, so back to the medium. Here's the big box here, and here's your first photon joining a next photon, and they're all building up here. Now, obviously, that's only 3, 4, 5, not very many, and when you get to the end here, that's going to be a bit pathetic. So the clever trick here, what you do is you have some mirrors. Oops, wrong side. So we mirror here, it goes along, bounces back, comes back into the box, builds up again, comes over here, and bounces back and builds up in more. Slight problem is it's never going to get out. So how to solve that? Brilliant. Piece of glass, you can go through the glass, but also it reflects a little bit as well. So rather than just have a normal piece of glass, they have what's called semi-silvered glass here. How do you draw semi-silvered? I don't know. Right, anyway, this mirror here is semi-silvered so that some of the photons bounce back in and some of the photons will escape. So anything escaping from this end of the tube is coherent laser light. Okay, light amplification, stimulated emission radiation. But there's enough bounces back to stimulate more, and it keeps going and amplifies more. But this end has semi-silver, so it can escape. Okay,